Welcome! In this session, we'll dive into LeetCode problem number 1792, Maximum Average Pass Ratio. This fascinating problem challenges us to maximize the average pass ratio by strategically allocating extra students across classes. Let's explore the problem, break it down, and solve it step by step. Stay tuned! In this problem, we are tasked with maximizing the average pass ratio across multiple classes after distributing a certain number of extra students. Each class is represented by a pair, pass_i, total_i, where pass_i is the number of students who passed, and total_i is the total number of students in that class. Additionally, we are given an integer extra students, which represents the number of additional students we can allocate across these classes. The goal is to distribute these extra students in a way that maximizes the average pass ratio. The pass ratio for a class is calculated as the number of students who pass divided by the total number of students in that class, and the average pass ratio is simply the sum of the pass ratios of all classes divided by the number of classes. The output should be the maximum possible average pass ratio, and answers that are accurate within 10 to the power of -5 of the actual value are acceptable. The output of this problem is a floating point number that represents the maximum possible average pass ratio after optimally distributing the extra students. Let's illustrate this with an example. Suppose we have three classes with the input classes equals 1, 2, 3, 5, 2, 2, and extra students equals 2. Here, the initial pass ratios for the classes are calculated based on the number of students who passed and the total number of students in each class. The goal is to allocate the two extra students in a way that maximizes the average pass ratio. The result in this case would be 0.78333, which is accurate up to 5 decimal places. In this example, the initial pass ratios for the classes are as follows. Class 1 has a pass ratio of 0.5, Class 2 has 0.6, and Class 3 has 1.0. The initial average pass ratio is 0.7. Now, we start allocating the extra students. First, we allocate one extra student to Class 1, increasing its pass ratio to approximately 0.66667 and raising the average pass ratio to 0.75556. Next, we allocate the second extra student to Class 2, bringing its pass ratio to approximately 0.66667 as well. This results in a new average pass ratio of 0.77778. Which is the maximum possible value for this input. Thus, the optimal allocation of the extra students ensures that the average pass ratio is maximized. Now, consider another example with the input classes equals 2, 4, 3, 9, 4, 5, 2, 10, and extra students equals 4. Initially, the pass ratios for the classes are 0.5, 0.33333, 0.8, and 0.2, respectively. The average pass ratio at the start is 0.45833. By distributing the extra students optimally across the classes, we can maximize the average pass ratio to 0.53485. This involves carefully choosing which classes to prioritize based on how much their pass ratios improve with each additional student. The final result is a floating point number that reflects this maximum possible average pass ratio. To summarize, the constraints for this problem ensure that the input sizes can be large, with up to 100,000 classes and students. The value of extra students can also go up to 100,000. The solution must be efficient enough to handle these large inputs while ensuring the result is accurate within 10 to the power of -5. There are also a few notable edge cases to consider. If all classes already have perfect pass ratios, adding extra students won't change the result. In a single class scenario, all extra students should be allocated to that class. Additionally, when the initial pass ratios are very low, the extra students must be allocated strategically to maximize their impact. These considerations are crucial for solving the problem effectively. To tackle the maximum average pass ratio problem, the goal is to allocate the extra students in a way that maximizes the overall average pass ratio across all classes. Since this involves optimizing fractional improvements, greedy algorithms combined with priority queues are a natural fit. Let's start with the brute force approach. The basic idea here is to simulate adding one student at a time to each class, recalculating the pass ratio for all classes after each allocation, and selecting the class with the maximum ratio improvement for the next student. While this method is intuitive, its computational cost is quite high. Specifically, for each extra student, you need to iterate through all classes, calculate the improvement for each, and then allocate the student accordingly. This results in a time complexity of O, extra students multiplied by the number of classes, which becomes infeasible when the constraints allow both values to be very large, like up to 100,000. For this reason, the brute force approach is not practical for solving the problem efficiently and was not chosen. To address the inefficiencies of the brute force method, we turn to the optimized greedy approach using a priority queue. Here, the primary idea is to allocate students in a way that maximizes the immediate improvement in the pass ratio. Instead of recalculating the improvement for all classes in every iteration, we use a max heap or priority queue to track the class with the greatest potential improvement at any given time. The pass ratio for any class is calculated as the number of passes divided by the total number of students. Adding a student increases both the numerator and denominator, leading to an incremental improvement. We can compute this improvement as the difference between the new ratio and the old ratio. By continuously allocating students to the class with the highest current improvement, we ensure a globally optimal allocation. The process involves computing the initial improvements for all classes and storing them in a max heap, then repeatedly allocating students to the top class, updating its improvement, and reinserting it into the heap. This approach is highly efficient, with a time complexity of O, extra students times log n, where n is the number of classes. It was chosen because it strikes the right balance between simplicity, efficiency, and scalability. An alternative approach that was considered involves using binary search to allocate students. The idea here is to iteratively adjust the number of students allocated to each class until all extra students are distributed. While this method might work, it introduces unnecessary complexity for this specific problem. Binary search is better suited for problems with a well-defined search space, but here, the dynamic nature of the improvements makes the heap-based greedy approach both more intuitive and more efficient. Ultimately, the optimized greedy method with a priority queue was selected as the preferred strategy. The key insight that makes this approach work so well is recognizing that the marginal improvement from adding students to a class decreases as more students are added. This means that by always prioritizing the class with the highest current improvement, we achieve the best overall result. The use of a priority queue ensures that the solution is computationally efficient and can handle the problem's constraints effectively, even for large inputs. When comparing the strategies, we see clear trade-offs. The greedy approach with a max heap is optimal and efficient, but it requires careful implementation, particularly in managing the priority queue. In contrast, the brute force method is straightforward and easy to understand but completely impractical for large inputs due to its prohibitive time complexity. The binary search method, while viable, adds unnecessary complexity compared to the greedy approach. In conclusion, the greedy approach with a priority queue stands out as the best choice for this problem. It achieves an optimal time complexity of O, extra students times log n, making it both scalable and efficient for handling large datasets. By carefully distributing students to maximize the overall pass ratio at each step, this method not only solves the problem effectively but also adheres to the constraints, providing the best balance between simplicity and performance. In this problem, we are tasked with allocating a given number of extra students to a set of classrooms in a way that maximizes the overall average pass ratio. Each class is represented as a fraction of passed/total, where passed is the number of students who have passed, and total is the total number of students in that class. Adding an extra student to a class increases its pass ratio, but the amount of improvement decreases as the class size grows. This diminishing return is a fundamental aspect of the problem. To solve this, we use a greedy strategy where the next student is always allocated to the class that provides the greatest increase in the total average pass ratio. To efficiently track which class offers this maximum gain, we use a max heap, or priority queue. This allows us to dynamically identify and update the class with the highest marginal gain after each allocation. By understanding how the diminishing returns affect the marginal gain, we can design an optimal and efficient solution using this greedy approach. To represent the problem computationally, we use tuples to store information about each class, specifically, passed, total. The heap is structured to prioritize classes by their marginal gain, ensuring we allocate extra students optimally. The algorithm begins with the initialization step. Here, we parse the input list of classes and compute the initial marginal gain for each class using the formula gain equals past plus 1 / total plus 1 past / total. This formula calculates the improvement in the pass ratio if one more student is added. Each class is then added to the heap as a tuple, where the gain is stored as a negative value to simulate a max heap, since Python's heap library only supports min heaps by default. Once the heap is initialized, we distribute the extra students. For each student, we extract the class with the highest marginal gain from the heap, allocate the student, update the past and total values for that class, and recalculate its marginal gain. The updated class is then pushed back into the heap. Finally, after all students are distributed, we calculate the final overall average pass ratio by summing the pass ratios of all classes and dividing by the number of classes. The final average pass ratio is computed by iterating over all the classes, summing their individual pass ratios, and dividing by the total number of classes. Let's now analyze the key operations and the overall complexity of the algorithm. During heap initialization, we calculate the marginal gain for each class and build the heap, which requires n log n, where n is the number of classes. For the student allocation step, each allocation involves extracting the maximum gain from the heap and updating it, both of which are logarithmic operations. Since this step is repeated for each of the extra students, it contributes extra students * log n to the total complexity. Finally, calculating the overall average pass ratio involves iterating through all the classes, which takes n. Combining these steps, the overall time complexity of the algorithm is n log n plus extra students * log n. The algorithm is also designed to handle edge cases effectively. For instance, if there's only one class, all extra students are allocated to it. For large classes, the algorithm accounts for the diminishing marginal gain and ensures floating point precision is maintained. Additionally, classes with zero initial passes are prioritized due to their significant relative gain when extra students are added. The pseudocode implementation provides clarity on how the algorithm proceeds step by step. First, we define a helper function to compute the gain of adding one student to a class. This function implements the marginal gain formula we discussed earlier. Next, we initialize the heap by iterating over each class, calculating its initial gain, and pushing it into the heap as a tuple containing the negative gain, past, and total. During the allocation phase, for each extra student, we extract the class with the highest gain from the heap, increment its past and total values, recalculate its gain, and push the updated tuple back into the heap. After all students have been distributed, the final step is to calculate the overall average pass ratio. This involves summing the pass ratios of all classes, which are stored in the heap, and dividing by the total number of classes. Throughout the process, the use of a max heap ensures that the algorithm remains efficient, even for large inputs. The pseudocode captures the entire flow, from initialization to the computation of the final result, and highlights the key operations that drive the solution. To further illustrate the algorithm, let's consider an example. Suppose the input classes are 1, 2, 3, 5, 2, 2. During heap initialization, we calculate the marginal gain for each class and store them in the heap as tuples, -0.166, 1, 2, -0.033, 3, 5, -0.250, 2, 2. The heap is structured to prioritize the class with the highest gain, which in this case is the class 2, 2, with a gain of -0.250. For the first allocation, we pop this class from the heap, update its values to 3, 3, recalculate its gain, and push it back into the heap. The updated heap now contains -0.166, 1, 2, -0.033, 3, 5, -0.083, 3, 3. This process is repeated until all extra students are allocated. The algorithm's greedy strategy ensures that each student is allocated optimally to maximize the overall pass ratio. Key optimizations, such as efficient heap operations and careful gain calculations, ensure the solution remains computationally efficient while maintaining accuracy in floating point operations. This combination of strategies allows the algorithm to handle even large and complex inputs effectively. Here, we start by importing the heap module, which we'll use to maintain a priority queue. The goal is to maximize the average pass ratio across all classes by strategically allocating extra students. To do this, we define a helper function called gain, which calculates the improvement in the pass ratio when one additional student is added to a class. This function takes the current number of pass students and the total number of students in a class, and computes the difference between the new ratio with one more student and the current ratio. Next, we initialize a priority queue, represented as a min heap in Python. To mimic a max heap, we push the negative of the gain into the heap. For each class, we calculate the potential gain from adding a student and push a tuple containing the negative gain, the current number of past students, and the total students into the heap. Once the heap is set up, we allocate the extra students. For each student, we pop the class with the maximum potential gain from the heap, add one student to that class, and update its past and total counts. After recalculating the gain for that class, we push the updated values back into the heap, ensuring the heap always contains the classes with the highest potential improvements at the top. After allocating all the extra students, we calculate the overall average pass ratio. To do this, we iterate over the classes in the heap. For each class, we add its current pass ratio, which is simply the number of passed students divided by the total number of students, to a running total called total_average. Finally, we return the overall average pass ratio by dividing this cumulative sum by the total number of classes. This gives us the maximum achievable average pass ratio after optimally distributing the extra students among the classes. Here, we begin the Java implementation of the problem by importing the necessary priority queue class. The main function, maxAverageRatio, takes an array of classes and the number of extra students as inputs. To manage our data, we use a max heap, which is implemented with a custom comparator. This comparator ensures that the class with the largest potential gain in the pass ratio is always at the top of the heap. To calculate this potential gain, we define a helper class called gain with a static method calculate. This method computes the difference in pass ratios before and after adding one student to a class. We then populate the heap by iterating over each class in the input array. For each class, we extract the number of passed and total students, compute the initial gain using the helper function, and add it to the heap along with the class data. This sets up our structure to efficiently allocate the extra students. Now, we allocate the extra students to maximize the overall average pass ratio. In a loop that runs for the number of extra students, we continually extract the class at the top of the heap, which has the maximum potential gain. We increment both the number of passed and total students for this class, as one student is added. Afterward, we recalculate the new potential gain for this updated class and push it back into the heap, ensuring the heap remains correctly ordered. Once all extra students are allocated, we calculate the final overall average pass ratio. This is done by iterating through the heap, summing up the pass ratios of all classes, and dividing by the total number of classes. Finally, we return the computed average as the result. To solve this problem, we start by defining a priority queue, or heap, that will store the classes based on their potential gain in pass ratio. The gain is computed using a helper function that calculates the difference between the new pass ratio after adding one extra student and the current pass ratio. Since we need a max heap but Python only provides a min heap, we store the negative of the gain to simulate the behavior. For the given input, we calculate the gain for each class. For class 1, 2, the gain is approximately 0.1667. For class 2, 3, the gain is 0.0833, and for class 2, 5, it is 0.0333. These gains are inserted into the heap, resulting in the initial heap structure where the class with the highest gain, 1, 2, is at the top. Now, we start allocating the extra students. In the first iteration, we pop the class with the highest gain, which is 1, 2, and add one student to it, making it 2, 3. We then recalculate the gain for this updated class, which is now 0.0833, and push it back into the heap. The heap is updated accordingly. In the second iteration, we again pop the class with the highest gain, which is now 2, 3. After adding one student, the class becomes 3, 4. The new gain is calculated as 0.05, and the heap is updated again. Once all extra students are allocated, we calculate the final average pass ratio by summing the pass ratios of all classes and dividing by the total number of classes. 4, 3, 4, the ratio is 0.75, 4, 2, 5, it is 0.4, and 4, 2, 3, it is approximately 0.6667. The average comes out to approximately 0.6056, which is our output. In this example, we consider a scenario where the classes are nearly full. The input consists of 3 classes and 1 extra student. As before, we calculate the initial gains for each class. 4, 3, 4, the gain is 0.05, 4, 4, 5, it is 0.0333, and 4, 2, 2, it is 0.1667. These gains are added to the heap, with 2, 2 having the highest gain. Next, we allocate the single extra student. The class 2, 2 is popped from the heap, and 1 student is added, making it 3, 3. The updated gain for this class is recalculated as 0.0833, and the heap is updated. After allocating the extra student, we calculate the final average pass ratio for all classes. The updated class 3, 3 has a pass ratio of 1.0, while 4, 5 has a ratio of 0.8, and 3, 4 has a ratio of 0.75. Adding these ratios together and dividing by the number of classes gives us the average pass ratio of 0.85. This is the output for this example. Moving on to the next example, consider a case where only 1 class is given. In the single class example, the input consists of 1 class, 4, 10, and 2 extra students. First, we calculate the initial gain for this class, which is approximately 0.0476, and add it to the heap. With only this class in the heap, we proceed to allocate the extra students. In the first iteration, we pop the class 4, 10, add 1 student, and recalculate the gain, which becomes 0.0404. The updated class 5, 11 is pushed back into the heap. In the second iteration, the class 5, 11 is popped again, another student is added, and the gain is updated to 0.0357. The class becomes 6, 12 and is pushed back into the heap. Finally, we calculate the pass ratio for the single class, which is 0.5. Since there is only 1 class, this is the final average pass ratio and the output. To analyze the time complexity of our solution, we can break it into 3 main steps. First, during heap initialization, we calculate the gain for each class using the gain function and push the result into the heap. Here, the number of classes is denoted by n. Each call to the gain function involves only constant-time arithmetic operations, which is O, 1. However, pushing an element into the heap takes O, log n. Since we repeat this for all n classes, the time complexity of heap initialization becomes O, n asterisk log n. Next, we allocate extra students to the classes. For each extra student, we extract the class with the maximum gain from the heap in O, log n, time, recalculate its gain after adding the student, and push the updated class back into the heap. Both the recalculation and the push also take O, log n. If we repeat this 4 extra students times, the time complexity for this step is O, extra students asterisk log n. Finally, at the end of the process, we calculate the total average pass ratio by iterating through all n classes in the heap, which takes O, n, time. These 3 steps form the basis of our time complexity analysis. When we combine the time complexities of all 3 steps, we get the following. Heap initialization takes O, n asterisk log n, allocating extra students contributes O, extra students asterisk log n, and calculating the final average requires O, n. Adding these together, the total time complexity becomes O, n asterisk log n plus extra students asterisk log n plus n. Since extra students can be as large as the number of classes, or n, the term O, extra students asterisk log n, dominates. Therefore, the overall time complexity simplifies to O, n plus extra students, asterisk log n. Shifting focus to space complexity, the heap stores up to n tuples, where each tuple represents a class with 3 values, the negative gain, the number of passed students, and the total number of students. Each tuple takes constant space, or O, 1, and since there are n classes, the total space required for the heap is O, n. In addition to the heap storage, the solution uses auxiliary variables such as those for storing the gain, the number of passed students, the total students, and the final average. Each of these variables takes only constant space, or O, 1. The gain function also uses O, 1 space for its calculations. As a result, the overall space complexity is dominated by the heap storage, which is O, n. For comparison, a brute force approach to this problem would involve iterating over all classes for each extra student, recalculating the average pass ratio for every class, and selecting the one with the maximum gain. This naive approach requires and extra students operations to process all extra students, making it significantly slower than the heap-based solution, especially when extra students is large. The heap-based approach, on the other hand, is far more efficient because it allows us to select the class with the maximum gain in log n time. This reduces the overall complexity from and extra students, with the brute force method to n plus extra students, log n, using the heap-based solution. In conclusion, the heap-based approach achieves a time complexity of n plus extra students, log n, and a space complexity of n, making it optimal for handling scenarios with a large number of classes and extra students. By leveraging the heap's logarithmic efficiency, we achieve a substantial improvement over the naive approach, which would struggle with scalability due to its linear time selection process for each extra student. One of the most frequent mistakes made in solving this problem is not prioritizing the class that can provide the highest improvement in the pass ratio. To avoid this, it's crucial to use a priority queue, specifically a max heap, which helps you efficiently track and allocate extra students to the most impactful class. Another common pitfall is the incorrect calculation of marginal gain. Remember, the formula for marginal gain when adding an extra student is pass plus 1, / total plus 1, pass / total. This ensures you're accurately evaluating the benefit of adding a student to a class. Additionally, edge cases should not be overlooked. For example, classes where all students have already passed, or scenarios where no extra students are available, need to be handled carefully to prevent errors. Simplifying heap logic is another tip. There's no need for overly complex heap structures. Using tuples like marginal_gain, pass, total, keeps your implementation clear and efficient. Lastly, be mindful of floating point precision errors, especially in languages like C++ or Java, where inaccuracies can creep in. Using Python's fractions of fraction or scaling values appropriately is a good way to maintain precision. Now, let's talk about key insights that can help during interviews. First, it's important to justify the greedy strategy you've chosen. This involves demonstrating that the problem has the optimal substructure property, meaning local optimizations, like allocating to the class with the highest marginal gain, lead to a global optimum. On the technical side, emphasize the efficiency of using a max heap. Each operation, whether extracting the top element or reinserting it after updating, runs in log n. Combined with iterating through the extra students, the overall complexity is extra students * log n. It's also beneficial to discuss trade-offs. For example, while a priority queue is clear and straightforward, you could explore custom data structures for specific performance gains, though this might complicate the implementation. Relating this problem to real-world applications, such as resource allocation in education or finance, can also leave a strong impression on interviewers. Lastly, practicing related problems can deepen your understanding. LeetCode 857, for instance, involves hiring workers with a similar greedy approach. LeetCode 502 focuses on maximizing profits under constraints, while 621 and 1383 both incorporate prioritization and heap-based optimizations. These problems share underlying principles that reinforce your ability to identify when and how to use greedy strategies effectively. Finally, let's consider alternative approaches and additional insights. One approach is brute force, trying every possible allocation of extra students to maximize the pass ratio. While this guarantees correctness, it's computationally infeasible for larger inputs due to its exponential time complexity. Another option involves using custom data structures, like a balanced binary search tree, instead of a standard max heap. This offers more flexibility for updating and querying classes but comes at the cost of increased implementation complexity. There's also the potential to explore dynamic programming to track allocation states. However, given the continuous nature of the problem, DP may not be the most optimal solution. The key takeaway here is that problems involving fractional optimizations, like this one, usually benefit the most from greedy algorithms and priority queues. Always focus on accurately computing marginal gains, as they are pivotal for maximizing global metrics. Lastly, building intuition through practice with related problems will help you quickly recognize when a greedy approach is appropriate, ensuring you're well prepared for similar challenges in interviews. Great job! We've successfully solved LeetCode problem number 1792 using a greedy approach with a max heap. Remember, problems like this highlight the importance of local optimization strategies and heap data structures. Thanks for watching, and be sure to like, subscribe, and share for more content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!